Thank you for the opportunity to present some of the results from the esophageal squamous cell carcinoma study. So just to give a brief introduction, although we've already talked about this a little bit this morning, esophageal squamous cell carcinoma is the initial focus for work package 1 of the Mutographs project. As you can see from the incidence map, there are areas of very high incidence in areas of Asia, including China and Japan, so also Iran and areas of East Africa. And we are aiming to collect from, well, it was 14 countries. I think one of those has now been lost from Paul's talk, but a significant number of countries from both high, intermediate, and low-risk regions. And the known or suspected risk factors for esophageal squamous cell carcinoma include alcohol consumption and consumption of hot tea drinks. So the title of my talk was From DNA to Mutation Signatures. So I'm not going to dwell too much on this technical aspect, but we do have a poster on the pipeline that we use at Sanger. So if anybody has questions on that, I would encourage them to see that poster. But just very briefly, the samples arrive at Sanger in DNA form, so they go through our core sequencing facility. The data is then imported into our analysis pipeline, and it has some QC, and mapping is done, and that's done by a central team. It then gets handed over to the Mutographs scientists, including myself, and the first stage is copy number analysis, which is done by 2 algorithms, ASCAT and Battenberg, and that is used to generate an estimate of tumor purity and a copy number profile. Now that information is used in the subsequent step, which is variant calling, to improve the accuracy, but one of the challenges that we found with some of the samples is that the tumor purity has been quite low, and esophageal squamous cell carcinoma is structurally very complex. And those 2 factors have meant that in some cases we've been unable to get a copy number profile that we think is accurate. And so basically samples are now going down one of 2 routes. They are going through a complete pipeline route, which means that we were able to get a copy number profile, and the tumor purity has been used to improve variant calling, and a partial pipeline route, which is we're using the tumor purity, but we can't use a copy number profile. So the majority of cases are still complete pipeline. That's 211 out of the 275 cases that we have currently, and 64 partial pipeline samples. And we've shown that although the number of variants is much lower in those partial pipeline cases, we can still use them to reconstruct a mutation spectrum which looks similar to cases of the same area. So here I want to show you a mutation spectrum. So earlier today you've seen pictures of mutation signatures, but a mutation spectrum is one step up. So this is all the mutations which are present in an individual sample. So you can think of it as a combined picture of all the signatures which are active in any particular sample. And I can't show you all 275 cases that we have, so what we've done here is we've created a cohort spectra. And that basically combines all the data from each place into a normalized average contribution to each mutation type. And these are the 96 context versions that you can see here. And what you can see is that across all of these high-risk regions, the picture is looking remarkably similar across all regions. There are some subtle differences, and I'm going to draw some attention to those, but overall, it is similar. So those were the single nucleotide variant versions. I also wanted to show you the dinucleotide versions of this. So this is where two bases next to each other in the genome are both mutated. And again, here you can see one spectra for each high-risk region, and they again look quite similar. However, you can see that the Japanese cohort in the scale is much higher than some of the other regions, so it goes up to 30% of the overall total mutation burden, whereas the others are around 15%, and this indicates that in Japanese samples there is some enrichment of some particular signatures. Now, as I said, these spectra are combinations of all the signatures present in samples, so we need a way to go from that combined picture to separate out the individual signatures. And you're going to hear a talk about this later today, so I'm just going to briefly introduce it. For Mutographs, the primary tool that we're using is Cig Profiler, developed by Lubmil's team. And basically, what this does is it extracts those signatures from the data, But when you have signatures which are commonly found together, and in this example you have the two APOBEC signatures which are found in most samples together, you can't always separate those two out unless you have a very large number of samples. But what Cig Profiler can do is then recognize that this is contribution from two different global reference signatures and split them out, so that then you can get an attribution data from both of those signatures individually, and as well as any novel signatures which have come out in the extraction. So these are the initial results from the latest train, which was released just a few weeks ago, so this is very preliminary analysis. I'm not going to focus on the details of the plot at the top, but essentially what you have here is you have increasing number of signatures being extracted and then a sharp drop-off. So we can see that we can be quite confident that there's not more than 15 signatures that can be extracted from the data at this current point in time. And this gets decomposed into 23 global reference signatures plus one new signature. However, this one new signature is found in a very small number of cases. We actually think that as the algorithm improves, this might disappear. It has very similar features to some of the reference signatures. And in the lower corner, you can see a heat map of those signatures at which we can extract. And again, we've grouped them into country so that you can get a clear picture of how things are changing, but overall it looks remarkably similar. This is not a perfect attribution. We know, for example, that we have some problems still with attribution of flat signatures. So, for example, signature 3 seems to be much higher than we would expect it to be. So we're not paying much attention to exactly the contributions of these signatures at this time, but I do want to just go through some of the signatures which we found and the patterns between the different countries. So firstly, signature 1. It's caused by spontaneous deanimation of cytosine residues. So you can see that up here, so this is the relative contribution of this signature to each case in the whole overall cohort. So you can see that on average it's contributing about 8.2% of mutations. It is found in almost all cases. It should really be 100%. In some small number of cases we can't see it because there is some extreme process which is contributing so many mutations that you just can't see signature 1, but it is present in all samples. Moving on to signature 2. So this is an APOBEC signature. I'm not going to explain too much about APOBEC because Mia is going to be giving a talk after me. But it's found at very similar levels throughout our 5 high-risk regions, found in the majority of cases, and is contributing on average about 10% of the mutation burden. Signature 5 is clock-like, which means it's associated with aging. It doesn't have a defined etiology currently. Again, it's found in most cancers in normal cells. We find it in the vast majority of our cases. The overall average relative contribution is about 23% currently, but this is one of the signatures which the attribution is probably going to change as the algorithm develops. But we're not seeing really much difference again between our high-risk regions here. Signature 13 is the other APOBEC-associated signature. Again, we find it in the vast majority of our cases, and the overall average relative contribution is about 13%. So overall, if we look at both APOBEC signatures 2 and 13, we're seeing that it's about 20 to 25% of the total mutation burden in each of our cases. And moving on to signature 16. So this is one of the signatures where we do see quite a big difference between our high-risk regions. And the etiology is unknown, but there have been some papers recently published which have linked it to alcohol consumption. And you can see here that it's very clear that it's present in 50% of our patients from Japan, but very rarely present in any other high-risk region, and very clearly enriched in that region. I'm not going to show any associations with the patient metadata, so my colleague Sergey, his talk follows mine directly, and he will be talking more about signature 16. So signature 18, found in about 65% of our cases overall, contributing about 12% of the mutation burden. Overall, the frequency is pretty consistent. There is a small drop in the frequency that we see it in Japanese cases. We probably need more data to see if that is a real association or not. And I briefly wanted to mention this signature, signature 22. It's found in a very small proportion of our cases. And signature 22, as you've heard earlier, is linked to exposure to aristoloic acid. But notably, of the cases that we find it in, 50% are from China, and overall we have a 10% frequency of this signature in the Chinese cohort. Where it is present, it's contributing quite low levels of mutations, so between 3% and about 11% of the total mutation burden. So if this is having an impact on the risk of esophageal squamous cell carcinoma in this cohort is unknown at this stage. We have too few cases. So that was the single base substitution Cig Profiler results. I briefly also wanted to show you the dinucleotide. Because the numbers of dinucleotide mutations are much lower, we don't get quite such a clear picture of what signatures there, but the current results, we can see 3 signatures are extracted, which then gets decomposed into 5 global reference signatures. And just briefly, we find dinucleotide signature 2, which is linked to various mutagens, DBS 4, 6, and 9, which have unknown etiology, and DBS 11, which we would really expect to see is associated with APOBEC activity. But if you look at this heat map, you should immediately be drawn to this point, which suggests that the signature which is enriched in the Japanese cohort is dinucleotide signature 4. And this is what it looks like if you look at the individual patients. So you can see that there is a much higher relative contribution in most cases from Japan. But it's not linked to frequency. So we see the signature in almost all cases. It's just that it increases there's a much higher mutation burden due to the signature in these cases. So we have now a situation where we've got increased attribution to signature 16 and DBS signature 4, both in the Japanese cohort. So we thought to ourselves, is this linked in some way? And in fact, it is. So if you have signature 16 present, you have a much higher attribution from signature dinucleotide signature 4. We don't know what this means yet, but it suggests that there is some form of link between these two processes. And it's true whether you look at the overall cohort, which is shown here, or if you look just in the Japanese cohort. So just to summarize, we can see that APOBEC activity is present in almost all cases of esophageal squamous cell carcinoma in these high-risk regions. What we don't know is what's driving that APOBEC activity, and that might differ between these regions, but the presence of this universal signatures possibly indicates a common molecular mechanism at play here. We can see that the Japanese cohort differs from other high-risk regions, increased contribution from SMV signature 16 and DBS signature 4. And all the data I've shown to you today is from these high-risk regions. So our priority is now sequencing from low and intermediate risk regions to compare to these regions, and also to start exploring the mutation signatures of higher context. So for example, the 1536, instead of considering one mutated base on either side, you consider 2 bases, and so forth. So thank you for your attention. Thank you to everybody who's been involved in this work, and I'm happy to take any questions.